So far, we've been doing what I'd call introductory material, all of linear algebra, and certainly what we talked about today, complex numbers and things like that. Today, we'll probably just get started with the real part of the course, which is analysis of systems and a little bit of understanding of control theory. So this is still elementary stuff, but you'll be actually doing some math, at least you'll be doing some calculus after all. And so maybe you'll get a taste of what it is. But I'll try to make it as easy to understand as possible. Okay, so far we talked about signals and the complex exponential signal, and hopefully you have an intuitive understanding of what a complex exponential signal is. It can be thought of as essentially a helix which goes through time and covers both the real and the imaginary space. Okay, what is a system? A system, from our perspective, is just something that operates on signals. So we can think of it as some kind of black box, and you have some set of input signals coming in and some set of output signals going out, and what's in the middle is the system. So the system is this black box, if you will, which is sitting over here, and it just converts signals, input signals to output signals, okay? And that's basically what a system is. So this definition is chosen very carefully to be as general as possible. And the reason we do it is because we want to analyze a number of different systems. Of course, when we think about a computer system, for example, we have in mind something quite different, right? We think of processor and memory, and think of a disk and network and all these other things. But that's not the system we're talking about over here. Here we're talking about a rather simple, simplified system which only has these very simple inputs and outputs. Okay, so the input is called the vector xt, and the output is called the vector yt, and these are vectors. So I'll draw the arrow line on top, actually the arrow on top. And actually, we're going to quickly get rid of vectors because it's too complicated. We'll come back to vectors when we talk about control theory, but for now, we're going to assume that these inputs and outputs are scalars, so we only have one single input and we only have one single output, and that's already difficult enough for now. And as I said, we'll get to vectors later, but now let's stay with this. And then we have I'm going to abuse the terminology and tell you that this system is associated with this function h, which I'm going to call I'm going to put it in quotes, transfer function. And it is, later on we'll discover that the term transfer function is reserved for a particular function, which is the Laplace transform of the impulse response. But for now, we're going to just this is the baby transfer function, if you will, where we say that yt is equal to h of xt. In other words, h is some kind of operator, and what h is doing is converting this input signal xt into the output signal yt in this fashion. So the system is defined to be basically h. Okay? So to make it clear, okay, there, we've got this. So this is a model of the system. We have a black box. We have one single input, the scalar function of time xt, the scalar output of time yt, the system defined to be the function h. And when you put a h dot, it means we don't really care what's inside. It's something. What that something is xt, and more precisely, yt is h operating on xt, and h is called the quote-unquote transfer function. Okay, so that's basically just setting up the terminology so that we can do something interesting with this. Okay, so any questions about this over here? Okay, so this is all should be familiar to you. All right. Okay, so we have, when you have a problem, when you have a system like this, we usually think of two problems. One is called the analysis problem, and the second problem is called the design problem. And the analysis problem is that we're given a system, any system, and we want to figure out what it's going to do. Okay, so we talked about last time. I talked about the Tacoma-Narrows Bridge and the one that oscillated and fell apart. So we want to analyze a bridge such as that and say, is it going to fall apart? Under what circumstances will it fall apart? That's the analysis problem. And in fact, in about half an hour, we'll see exactly what made it fall apart, actually, mathematically speaking. And the second part is, how do you prevent it from happening? That's a design problem. Okay, so we'll talk about both. How do you do analysis? How do you do design? This part is usually called systems analysis. Okay, and that's what we're going to do in this chapter. And the second part, the design problem, is usually called control theory, because you're going to control the system, and we'll get to that later. Okay, so we're not going to do any design, we're just going to do an analysis. Before that, it's good to have some terminology in place, and so I'm just going to quickly go through some terminology that we associate with our study of systems. And they are so we have systems that are continuous, just like we have signals that are continuous and discrete. We also have systems that are continuous versus discrete. So continuous systems are going to look at, basically we're going to have the input signals are continuous, the output signals are continuous, so it's a continuous system. In a discrete system, the input signals are discrete, I should say discrete time, to be more precise. And this is continuous time. This is, we're talking more about the time rather than on the values that are being assumed. The values in the continuous time system, the values that are being assumed of these signals can change at any point in time. They don't have a clock associated with them, so it's continuous time versus discrete time. And similar to signals, we also have analog versus digital. And these are the this is associated with the time, and these are the values associated with the signal. So in an analog system, the signal can take any real value, whereas in the digital system, the signal can take only one of a finite set of values. Okay, so for example, if you're going to represent the signals with a 16-bit number, you can take 65,536 different values, and that's a 16-bit number. And so it's a digital system, because maybe you have 16-bit numbers to deal with. Whereas if you have a system which is not which is an analog system, the inputs could be any real. So imagine that you have some kind of bicycle pump, you push down on it. The amount you push down is not quantized. Okay, you can push down any arbitrary real amount, and so we'll call that an analog system. Okay, so that's the difference between an analog and a digital system. In a digital system, the bicycle pump would have exactly like 16 levels, or and you can push down one of 16 levels, and in between you can't push it down. So that would not be what we have in an analog system. So the signals are, that's the values taken, and then to take the bicycle pump analogy, in a bicycle pump you can go basically any time, right? Whereas in a discrete system you have a clock. Every time the clock ticks, you can push only at that time. Okay, so if you had a digital bicycle pump, it would be rather jerky. It would be like a movie. They would go like this, something like that. So as you can see, I pumped my bicycle this morning, so that's why I'm thinking about it. But a discrete time bicycle pump would be like an old-fashioned movie. If you've seen those, you go like that. Okay, anyway, so we don't do that. That's a discrete system. Okay, more interesting terminology. This is different from signals now. So we have something called causal systems, or versus what are called acausal. Causal system means that it only acts on the past. It can't act on the future. Okay, so when I have a system, I might have a system which only acts on inputs from the past. Okay, I can't act on future inputs. So you're saying, of course, that's what happens in real life. How can you have a system which is acausal? How can you design a system that works in the future? And the answer is, well, we could work on traces or logs, right? I could take a system, create an output trace, a simulation, and in the simulation, I could look at both past history and the future to do something, right? Or for those of you who studied cache replacement policies, right? How many of you looked at studied cache replacement policy, and you know that what is optimal in a cache replacement policy? Anybody remember that?
Don't know.
You don't remember.
There's like least frequently used.
The least frequently used is a causal algorithm. The optimal for cache replacement. Who can tell me the answer? Yes?
You want to throw out the one that's not going to be used for the longest?
That's correct, but how do you determine that? What's the optimal cache replacement policy? Yeah, Muhammad?
You should see the future
Yeah,
and guess what's going to be used.
that's right. So if you know the future, you know the one that's going to be used furthest away in the future, right? Because you know the future, so you actually work backwards, okay? And so if you just go backwards in time, then you just figure out, the one that's going to be used the latest, you know it, and then you throw that out because you're not going to use it, right? So it's acausal, right? So if you had a log and you wanted to study the optimal cache replacement policy, it's acausal. So any real system is going to be causal, but we can do acausal systems. You can build them over logs, right? For example, cache replacement is the optimal cache replacement policy is in fact acausal. Okay, then we have a system called memoryless. Memoryless versus dynamic. And a memoryless system is one where you act only on the inputs represented at that particular point in time. You don't really care about what happened in the past or what's going to happen in the future. You have particular input, you do something right away. Okay, and that's memoryless. Whereas if you have a dynamic system, you have some state, you have some memory, and when you have state, life becomes very hard because you got to now worry about what happened in the past and then what happens in the future. Memorylessness is like this Markov thing I talked about earlier. Memorylessness says I got a particular point in time, and what happens in the future doesn't depend on how I got there. It just depends on what is there right now. And whereas in any system with a dynamic system, that's a technical term, dynamic system means I have some state, I have some RAM, whatever. And so what happens in the future depends on what happens in the past, which makes it more complicated. Then we have something called a time invariant system. Versus, what's the opposite of that? I guess, no, I don't know. Non-time invariant, I don't know. Or time variant, okay. I don't know. We have never, okay, so time varying, I guess. And a time invariant system means the model parameters, the system parameters don't change over time. Okay, I fixed it. Once I know what h is, the h is the system, right? So I don't have h as a function of t, okay? H is a constant, whereas in a time variant system I'll have like a sort of ht. So at some point it's like that, and it changes, it becomes something else. That would be. We typically assume that systems are time invariant, okay? Time invariant, of course, they may be dynamic, they may have some memory internally, but in reality, systems are time variant. And the reason is because there's what's called wear and tear, right? So we have, for example, you take a system like a bicycle pump, again, I'll continue with that. So when you push down with a particular force, we're going to have a certain air pressure that's going to come out the tip, where you're pumping the air in, right? But with wear and tear, you have leakage, okay? Because the piston is made of some kind of rubber or plastic or whatever. The piston is going to leak. When the piston leaks, what happens is the output pressure at the end, where you're filling up the air, is going to be less than what you started out when you bought it new. That is a time variant system, and in fact all physical systems tend to be time variant because the parameters do change over time, but again that makes it very hard to analyze. So for most purposes we're going to assume that the model parameters are going to be fixed, but you have to remember that in real life there is wear and tear. Things do change and you have to kind of worry about that. I mean, when we talk about control theory and control systems and robustness, we'll take that into account. Okay, and then we have this notion of linear system. And the linear system has got two properties. One is scaling. It's also called homogeneity. And the second thing is called additivity. And let's kind of just say that, so we're saying that if for scaling, we can use the h notation now. We're saying if y1 is equal to h of x1, then if you take h of kx1. In other words, the input is scaled by factor k, then it's just like multiplying the output by the value k. You're just going to multiply it out by the same value. So if you again, with my bicycle pump analogy, if I push down 10 times harder, then the air velocity is going to be 10 times faster, okay, at the output. That's exactly linear scaling, right? So that's the scaling. In practice, no system is going to have this. Right? Why? Because every system has a kind of a tolerance. It has a range. Beyond that, it can't go. So, I have a pump and I push down 10 times, or I push down 1,000 times more, it's just going to collapse into bits, okay? I mean, it's like putting a hydraulic press and using that to press a bicycle pump. What's going to happen? It's just going to smash it to bits, okay? It's not going to work. So this is nice mathematically. In practice, it never works, but we'll pretend it's okay, for now, okay? We'll just pretend everything is fine, and scaling is going to be true. So then ky1 is going to h of kx1, and additivity is exactly what you would think it is. Okay, if y1 is equal to h of x1 and y2 equals h of x2, then this implies that y1 plus y2 equals h of x1 plus x2. So we have two inputs, okay, at different points in time. Okay, I pressed on a little bit, I pressed on the harder, and if I sum them up, it still looks like, even the output looks like what the inputs were. Separately, I can add them up. Okay, and that's what's called, that's what we call additivity. Okay, right. And I forgot about time invariance. So time invariance basically means if that I should put. Let me just show the math for this, which is that if y t equals h of x t, then if you make this going to be, if you make that time shifted, so it's hx of t minus tau, then it's going to be y of t minus tau. So right shifting the input by a certain amount of tau steps in time, or tau time instance, is going to be, the output is going to be time shifted by the same amount. So if I do it later or earlier, the output is going to be delayed or less delayed, pulled forward in time by the same amount. Okay, so that's the value over here. So if we take these two conditions of homogeneous scaling and additivity, we have a sort of a special property called superposition. And superposition basically says that, I'll just write it out, if y1 is equal to h of x1, and then y2 equals h of x2, and then k1 y1 plus k2 y2 equals h of k1 x1 plus k2 x2. And what we're doing is just essentially combining scaling and additivity. We get superposition, and that's the property that we have over here. Okay? A system is said to be linear if it obeys superposition. So if it obeys superposition, then we're getting sort of these two things. Because remember, linear system is scaling and additivity. Scaling and additivity lead to superposition, so this gives you linear. Okay? And that puts me just in right time to show you the solution to the homework problem. So there we had the following problem. Okay, I'm going to keep this over here. Okay, so the system was y equals, I was going h equals ax dot plus bx plus c. So it has a derivative, which is fine. And so we can just run through the math kind of straightforward. So we try the superposition property to see what this. So first of all, is it time invariant? It is time invariant because h doesn't change over time. So certainly it's time invariant. What about linearity? We're going to test the superposition. So we say that y1, so k1 y1 equals what? A x1 dot ka x1 dot plus. Okay. So how am I doing this? Okay. Better for me to just follow my notes here. So let's do this step by step. So y1 equals ax1 dot plus bx1 plus c, and y2 equals ax2 dot plus bx2 plus c. This is by definition, right? This is just definition. I haven't done anything special here. Now, I can multiply this by k1, okay, to get k1 y1 equals k1 times ax1 dot plus bx1 plus c, and then similarly k2 y2 equals k2 times ax2 dot bx2 plus c. Okay. Now what we want to do is we want to add these two guys up. So k1 y1 plus k2 y2 is equal to the sum. So k1 a x1 dot plus k2 a x2 dot plus k1 b x1 plus k2 b x2 plus k1 c plus k2 c. Okay, so we've computed basically k1 y1 plus k2 y2 as this guy over here. Now, by definition, let's compute h of k1 x1 plus k2 x2, right? Because for superposition, what did we say? That k1 y1 plus k2 y2 equals h of k1 x1 plus k2 x2. So we just plug that in. And this one turns out to be a times d by dt of k1 x1 plus k2 x2 plus b times k1 x1 plus k2 x2 plus c. Okay? All right. And right away we have a problem. And the problem is that this term over here doesn't matter what these terms are. This term over here is going to be c, and this term over here is k1c plus k2c. And so it's not linear. Okay? It's not linear. It's a nonlinear system because it doesn't satisfy superposition. And so it's a trick question. Okay? If you were just kind of doing it blindly, you would get the wrong answer. So hopefully you've seen that. So what's really going on is that this term is what's causing you the problem. This term over here. If this one goes away, then it's linear. So when you look at a differential equation, any differential equation with a constant term in it like this is going to be nonlinear, okay, because of this. Because you're always going to have this problem no matter what, okay? So it's a nonlinear time invariant system. So that was the answer to the first question. And I'm going to do the second answer and then take a break. So any questions about this? I've tried to make, yeah?
You have always, in general, defined a linear system such that it has C.
It has what, sorry?
When it has C in general, we can surely say that it is not linear, and when it doesn't have C.
No, I'll talk about the general form of a differential general differential form of a linear system in about 20 minutes. Okay, and it's actually, you probably should have read it by now, but it doesn't have a constant term in it. Okay, if it has a constant term, you will find that the differential form is not going to work. The differential form cannot have it. So the second question was actually pretty straightforward. It said, what is the output of the system when the input is equal to e to the minus 0.5t. Well, so the output is h of x equals h is going to be a d by dt of e to the minus 0.5t plus b times e to the minus 0.5t plus c, right? That's by definition. So yt, and that's equal to minus 0.5a e to the minus 0.5t plus b e to the minus 0.5t plus c. So that's the answer. Right? It's very simple. You're simply applying h to the input. We get the output. Okay. So hopefully with these two questions, you have a sense of what a system is and what a linear time invariant system is. A linear time invariant system satisfies superposition and time invariance. And that makes our life much easier. So basically, we're going to work only with linear systems. And if they're not linear, because of wear and tear, so the model parameters change, or because it has a maximum or something, then we do something called linearization. And I'll discuss linearization in some more detail when we do control theory. But generally speaking, what we do is we find a particular operating point, and any system, any function can be expanded with a Taylor series around any operating point. So choose the operating point, we find the Taylor series expansion, we take the first two terms, throw away the rest because those are not linear, and we end up with a linear system. So we can always linearize a system by using the Taylor expansion. But we'll talk about that later. The first thing is, what happens when we take a linear time-limited system and we give it a complex exponential input? Okay, we're going to give it a special input, but it's going to be a complex exponential input. The second thing is, what happens if we give it no input at all? Just don't give it any input at all. Or to be more precise, we don't give it any input after time 0. We could have some input exactly at 0, but not beyond. And then finally, what happens when you give it an arbitrary input? So those are three things we're going to study. And all three, the answers are quite interesting. So let's start with what happens when we give it an input over here. So we know that yt is going to be h of xt. And we're setting that xt is equal to k e to the st, where s is a complex value. So s is of the form sigma plus j omega. And this is what we looked at last time. So this was either a exponential or the helix or the sinusoidal or whatever. So this is actually quite a large number of things. It can be even the constant, right? Because the exponential can be constant and could be real, complex, all these great things. But right now, so this means that yt is going to be h of, we're just going to plug this in here, k e to the st. Fine. So far, so good. Now what I'm going to do is I'm going to consider the following scalar. It's a scalar with respect to t, okay? And that is a scalar e to the s tau. Okay, so tau is something, doesn't matter what it is. It's some real value, it's not complex. S is complex, of course. So I have a scalar with respect to t, which is e to the s tau, and I'm going to multiply that with this input. So I'm going to get h of e to the s tau k e to the st, and that's going to be the output, right? Now this system is LTI. So what do we say when it's LTI? If you multiply this by a scalar, then it's going to be coming out on the output as a scalar multiple. So the output is going to be e to the s tau yt, right? Because I multiplied the input by a scalar value e to the s tau, so the output is going to be multiplied by the same thing, right? All right. So what we see over here is that this e to the s tau yt. Okay, so let's look at this one over here. This one over here can be written as h of e to the s t plus tau, right? Because that's just the way exponentials work. E to the st plus tau is what we get over here. Now if you look at this one over here, this looks like a time shifting by tau steps to the left, okay? Right? So this one is going to be e to the st plus tau is a time shifting of the time value by tau steps, constant number of steps to the left. And by definition, this is going to be y of t plus tau. Because if I erased it, but what superposition told us, what time scaling told us was that if we move the input x by t plus tau, okay, then y is going to move by the same amount because it's time invariant. Okay? So there's no magic here. All this is, so the only thing is I changed the left-hand side over here, right? And so these two left-hand sides have got to be equal. These two left-hand sides have got to be equal because this thing hasn't changed. This is just rewriting the expression. So if this is equal to this, and this is equal to this, and then this must be equal to that. Okay? It's got to work. So that means e to the s tau y of t equals y of t plus tau. And this is going to be true for all values of t. Because this is a general equation, so it's true when t equals 0. It's going to be true, right? So that means that e to the s tau y of 0 equals y of tau by just setting t equals 0. Okay? This is just kind of manipulating the equation by setting t equals 0. I'm going to go over this one more time because I can see quite a few of you confused. And now the last thing to get this to really shock you, I guess, is to take the derivative of that with respect to tau. So I'm going to differentiate with respect to tau, not t, with tau. And I get dy tau by d tau, okay, equals, sorry, not that one. I was going to differentiate, oops. Okay, I'm going to differentiate this one with respect to tau. It's not that one. Dy tau by d tau is equal to s y 0 e to the s tau. Okay. So dy tau by d tau is this one, and the derivative of this with respect to tau is s e to the s tau. So I get s e to the s tau, and I get y0 over here. But then I know that e to the s tau y0 is going to be yt. So it's going to be, sorry, it's going to be y tau. So it's going to be s y of tau, where I just plugged in e to the s tau y0 equals y tau. So e to the s tau y0 equals y tau. I just plugged it in. So this is what I get. dy tau by d tau equals sy tau, which is a first order homogeneous differential equation, right? And the standard solution for this is that y tau equals some f of s, some function of s, e to the s tau, or I can write it in terms of t, y of t equals f of s e to the s t. So where f is some function of f is independent of t but may depend on s. Okay, so I'm going to just go through this one more time because I'll just start with a simple thing. S is some complex quantity and xt is k to the st, right? So that's the complex exponential input. So this is by definition yt equals h of xt, and so yt equals h. This is by definition. We get this. Now we introduce a special term which is a scalar with respect to time called e to the s tau, some scalar, some complex number, right? You can always expand this as cos of s tau, plus sine of j sine of s tau. So it's some complex number. I'm going to multiply that on both sides, okay? Because it's a scalar, I can multiply that on both. Well, to be more precise, I'm multiplying the input by this scalar, and this is by scaling. Scaling implies that by multiplying the input by this scalar value, the output is going to go here. Time invariance implies that this value, which can be viewed as a time shift by tau, results in the output being time shifted by tau. Right? So scaling and time invariance, which both, this comes from linearity. Okay, so linearity and time invariance show me that these two therefore should be equal. And if these two are equal, we get this equation over here. And if we say t equals 0, we get this equation over here, which is that e to the s tau y0 is y tau. And if we take the differentiate this respect to tau, I get this one, dy tau by d tau is sy0 e to the s tau. And then I just replace this over here. I get y tau is f of s e to the s tau, or yt is f of s e to the st. So What I've done so far is just like basic undergrad calculus, this